Good morning, class. I hope you remember last year that we talked about domain and range. Domain is all the x values of a function, and range is simply all the y values of the function, just like you see in this image right here. Now we have an example here. If I want to find the domain and range of this function, the domain would be all the x values. So I'm writing out all the x values 2, 3, 4, 5, and 6. And the range would be all the y values of the function, which is 10, 10, 20, 30, and 60. That's simply domain and range. Something else we talked about was interval notation, and I hope you remember that a curly bracket means that that value or that number is included, but a curly bracket means number is not included, and square bracket means number is included. So for this first one, it's been done for you. If you have a value that's greater than a, then the solution set for that x would be that curly bracket a, because a is not included because x is greater than it, and then infinity close brackets with the curly brackets. The next one, less than a, would be minus infinity up to a. Let me try to do this one right here in this box. So, and I hope you can fill out all these others. If this means a is not included, so curly bracket a, and this less or equal or greater or equal for b means b is included. So I hope you can see really quickly that all these others come to the different things that you're seeing on your screen. The three types of notation, again, we talked about these last year. We have the inequality notation, where you write something like an inequality, just as you see here. X is between 1 to 3, both values included, or, in this case, union. Just like we talked about sets, union means all the things in this set plus all the things in that set. That's the same thing that OR means. That's inequality notation. Another type is the set builder notation, and again we talked about this last year, simply meaning this says x is such that x is between 1 to 3, with both of them being included because of the equal sign, or you can see it as a union of sets, x is greater than 5. That tells you all the characteristics of the elements of this set. Another notation which we're going to look at very importantly is the interval notation, which we've just described a couple of slides ago. The square brackets mean that the values 1 and 3 are included, and the curly brackets mean that 5 and infinity are not included. Let's look at some practice examples using graphs, general shape graphs. Now, we're calling them parent graphs because they are like general shape graphs. If you have a graph that looks like this, the domain would be all the x values that can fit on that graph. The range will be all the y values for that function. Now, if you look at this one, the curve goes on endlessly in both the x, positive x and negative direction. So that means the domain will be from negative infinity to positive infinity. In terms of the y-axis, this graph does not continue indefinitely. It has only one constant y value. So the range will only be that constant y value. If this graph was 2, then this range would be simply 2, 2, or just the number 2. Another common graph is you have a positive slope graph like this, or it could be a negative slope graph. These arrows show me that it's continuing indefinitely in the positive and negative direction. So my domain is going to be negative to positive infinity. And at the same time, these same arrows show me that this graph continues indefinitely in the positive and negative y direction. So my range is also going to be from negative infinity to positive infinity. We're using the curly brackets because negative and positive infinity are not included in the solution, but it just shows you how far the graph goes. This is another one, an absolute value graph. This means we're only interested in the positive range values of this function. So -1 magnitude would give you a positive value for y. So this is what the graph would look like. Again, these arrows show you that it's continuing indefinitely, positive and negative. And since I don't have anything in the negative side of the y-axis, that tells me that the range is only positive values starting from 0 going upwards. So the domain would be negative infinity to positive infinity, but the range will only start from 0, 0 included, because the graph touches 0. Moving on, another type of graph is the quadratic graph. This is also another one where it's continuing indefinitely in the positive and negative x-axis, also continuing indefinitely in the positive y-axis. So the domain is going to be similar to what we've seen before, but the range is only from 0 to positive infinity. Another type is the cubic graph. Again, following the same idea, continuing indefinitely, so that's simply going to be negative to positive infinity for both the domain and the range. The reciprocal graph. Now, this one is an interesting one, because when we look at the expression 1 out of x, there are some values for which this function could be undefined. There are some values for which it could be undefined. So first ask yourself, what value of x is going to make this denominator 0? Because if that denominator is 0, the function will be undefined. To get that, I will solve for the denominator by equating it to 0. I can see that if x is equal to 0, the function is undefined. So the domain cannot include the value x equals 0. That's why on the graph, x equals 0 is this line right here. You do not see the graph touching that line. It continues close and close and close to the line, but it never touches it. And in math, that's called an asymptote. But that just shows you that 0 cannot be part of the domain. On the other hand, on the range, again, 0 is not part of the range because the curve does not touch that line y equals 0. So my domain is going to be from negative infinity to 0, union or plus from positive infinity, from 0, to positive infinity. I hope you can see that these domain and range descriptions do not include the value 0. It's like 0 has been knocked out of the domain and the range. Same idea here. If I have x equals 0, the function will be undefined. So 0 is not part of the domain. And at the same time, 0 is still not part of the range. So that would look like the same thing. Sorry, the range, 0 is not part of the range. And according to this function, we don't have any y values below the 0 line. So my range will only be from 0 to infinity. Moving on, the square root function, again, continues indefinitely. So this this domain will be from 0 to positive infinity. 0 is included, yes. But the range, again, will also be only from 0 to positive infinity. 0 included, infinity not included, just like this. Now, a special thing to note about square root graphs is, ask yourself, because you know that you cannot take the square root of a negative number, so ask yourself, you know that from the beginning, anything inside the square root has to be greater or equal to 0. So when you solve this expression, it will tell you what values of x can be in the domain, what values cannot be in the domain. We're going to see this easier in another example that we'll look at. This is a constant cube root function. Again, look at that. Shows you it continues indefinitely. So the domain and range will be pretty easy to work out. All right, so let's find the domain and range of this function. An easy step is to first graph it using Desmos. So I graph it with Desmos and I put it here. I hope you can see that the x values continue indefinitely. So my domain will be negative infinity to positive infinity, not included. and my range, there's nothing below -1. Everything in terms of y values starts from -1 and goes upward. So my range will be -1 up to positive infinity. Remember, square bracket means included, curly brackets means not included. And this is another one where the denominator can get funny. In order to know what values of the function make this function, what values of x or what values of the domain make this function undefined, I need to solve for the denominator by equating it to 0. When I equate it to 0, I can see that x equals -1 would make this function undefined. So I know immediately that -1 cannot be part of the domain. And I think you can see here, because if I draw the line x equals -1, the graph never touches that line. It goes close and close to that line, but it never touches it. So my domain will be everything from -infinity, because it continues going, up to -1, not included, and or union everything from between -1 and positive infinity. My range, on the other hand, if you look at this graph, this line y equals 0 does not touch the curve. It's an asymptote. So my range will be everything between -infinity to 0 and or union everything between 0 and positive infinity. Please don't forget that curly brackets not included, square brackets included. This is another one where we have a square root function. Since it's 2 root x plus 4, remember we cannot take the square root of a negative number. So you want everything inside here to be bigger than 0. So I'm going to first solve for x plus 4 greater or equal to 0, because that's what it must be. For this function to be valid, for it to have real roots, a real square root, this expression has to be greater than 0. When I solve for it, I think you can see that x must be greater than -4, greater or equal to -4. So the domain for this function must be greater or equal to -4. The domain will be -4 up to infinity, -4 included up to infinity. And the range, I hope you can see from the graph that the range is any value that's above 0, because I cannot get a negative value from squaring something, from taking the square root of something, sorry. So the range will be from 0 included up to positive infinity. Piecewise functions is the last thing that we're looking at today, and you can have functions that have different outputs, that have different domains for each section of the output. So piecewise function is one in which more than one formula is used to define the output. Each formula has its own domain or set of x values, and the domain of the function is the union of all these sets of smaller domains. I hope you can see from this one that this function has a different formula for the output when x is less than 1. Then between 1 and 2, it has a different formula. And then from 2 onwards, it also has a different formula. What does this look like? Let's see on this graph. So first of all, first identify or clarify that this is what the domains would look like. The green section of the graph will have its own graph. If I was drawing x squared on its own, it would look something like this. X squared. That's what it would look like. Something like that. But this tells me, this restriction of the range that is right here, tells me that that green portion of the graph, that portion x squared of the graph, is only true for when x is less or equal to -1. So I'm only going to draw that graph, oops, very big. I'm only going to draw that graph undo for x less than -1. So I'm only going to draw it, I'm going to erase it from there, and I'm only going to draw that graph up to here, because that is the value x is equal to 1. anything beyond that 1, so starting from here, this way, the graph is valid. But onward, the function does not have that definition in the preceding domain or in the preceding range of x. What definition does it have? This function is 3. It takes on a value of 3 between 1 and 2. 1 not included. So this function takes on a value of 3. This is so this is 0, 1, 2, 3. This function takes on a value of 3 between 1 and 2. Now I need to specify that because right here, in order to show that 1 is not included for that section of this function, I'll put that circular thing, the circle, and then the line starting there. That's what it would look like. So that's what it's supposed to look like there. And then at the end, it touches the line x equals 2. Moving on. The same function has a definition of x for x is greater than 2. When x is greater than 2, the function is basically y equals x, right? And I know you remember that y equals x is simply the line, the positive gradient slope line like this that passes through the origin. So I know that for x greater than 2, this is 1, this is 2, the line y equals x would have been the line that passes through this, like this. Would have come like that, like that, like that, like that. Hope I got it right. That's what it would have been like. But because it's only true for x greater than 2, I'm going to erase it and then show what it looks like for x greater than 2. So this is 2, x greater than 2, that line, it cannot be here, can't be there. Starting here, this is what it would look like. I hope that's clear. I'm going to try to show it to you on Desmos. So if I have my Desmos, this function is, you remember it, function is x squared 3 and x. So it's x squared, but that's only true when x is less than or equal to 1. That's what it looks like. And then it's 3, but only between 1 and 2. And then it becomes y equals x for x greater than 2. That's what it would look like. Now I'm using Desmos here, but on top of using Desmos, you should be able to draw this piecewise function on your own. So this is what the function would look like, and I hope I've done an okay job tracing it out. So I hope you can see that that's a piecewise function. It's simply a function that has a different definition for each section of the domain. Kind of like, some of your friends on Monday, they look like this, or they, you know what I'm saying? People are different depending on circumstances. So in one way or another, all of us are piecewise functions. Here's another example. I have a piecewise function like this, x cubed if x is less than -1. The function is 2 if between 1 and 4, and the function is the square root from when x is greater than 4. So what would that look like? Remember, we looked at the parent graphs, and you saw how to draw the graph of a cubic function. I hope you remember that a cubic function kind of looks like this, right? And so that would be this first one. This second one is just a constant function, so we'll have a straight line like that. And this third one is a square root function, so it would be something like this. Now I'm going to draw these sketches on this graph just for the defined domains. For the first domain, since I know it's supposed to be something like this, I'm just going to draw a sketch. I'm not going to try to see the exact positions. And I know that's only true when x is less than 1. So everything that is greater than, when x is less than -1. So everything that's greater than -1, I'm going to erase. This is -1, So I'm going to erase all this going up. And I'm going to put a little circle to show that -1 is not included. The function is 2 between -1 and 4. This is 0. Let's do a better job of erasing. This is 0, this is 1, this is 2. The function is 2 between -1 and 4. So between -1 is right here. Let's use this. Yeah, that's better. Where were we? It was like this for the cubic function, but I took out everything beyond -1. All right. Now, remember I put the circle to show that it's not included because this is just a less than sign. If it was less or equal, I wouldn't put that circle. You guys can do a better job at sketching this. Between -1 and 4, sorry, this is supposed to come all the way -1. So between -1 and 4, the function takes on the value 2. So 0, 1, 2 takes on the value of 2 between -1 and 4. Again, both not included. And after that, it takes on the definition. Beyond 4, it takes on the definition of the square root function. Now remember that a square root function initially was supposed to look like this, right? But it's only going to look like that for this particular piecewise function for values of x that are greater than 4. Now that means I'm going to erase it from here, and I'm also going to erase it from there. And I won't forget to put the little circle to show that that value 4 is not included. So this is what my piecewise function would look like for this graph. Again, I'll try to show you on Desmos. X cubed -2 and root. So this one is x cubed, so this is for x less than or equal to, no, less than 1. -1, sorry. And it is 2 between -1 and 4. And it is square root of x between, for everything that's greater than 4. Square root of x for x greater than 4. Again, I hope, my sketch was a pretty good job at it. If not, don't blame me too much. So yeah, that's what it would look like. This is what your piecewise function would look like. This is a curve. It's not appearing very curved right here. This is what it would look like, and this is what I had drawn. So yeah, I wasn't using the super accurate. Wasn't being super accurate. Right. So there you go. That's the piecewise function that's the piecewise function. All right. So we've talked about piecewise functions. We've talked about domain and range. You guys can go ahead and complete this homework and the class notes from pages 3 to 5. All right. Bye.